Hello, and thanks for joining McObject for the webinar, Databases, Make or Break Technology Choices for High-Performance Applications. First, McObject CEO Steve Graves will take you through our main presentation, which examines the important technology choices that can lead to better performance, efficiency, and reliability in a real-time application. After that, we'll have time for questions based on the presentation and about database technology generally. You will be able to submit questions using the Q&A window in the lower right corner of your screen. And now, to get the show rolling, I'd like to introduce McObject's Chief Operating Officer, Chris Murine.
Thanks, Ted. Hello, everyone, and thank you for joining us for our webinar. We have a very interesting session for you today. When you're developing high-performance applications, your database management system must be able to deliver results superior to standard enterprise DBMSs. Database qualities such as microsecond responsiveness, the ability to process mountains of data without constant tuning, and the development flexibility to will make a tremendous difference. But the sheer volume of database technology options, such as in-memory versus on-disk storage, client-server versus in-process architecture, and varying application programming interfaces can be huge and can significantly affect your final results. In our session today, we'll explore these options and provide a roadmap for selecting the best solution for your needs. McObject was founded 9 years ago with the unique goal of bringing to the market a highly optimized DBMS for in-memory usage, thus eliminating the need for homegrown data management tools. Since our inception, our high-performance products, ExtremeDB and PERST, have been used in applications including networking, consumer electronics, medical, military and aeronautics, embedded controllers, and many other vertical solutions. This success has fueled our growth with staff and customers in locations throughout the world and millions of applications which have shipped using our technology. I'd like to introduce you to Steve Graves, our co-founder and CEO, who will be covering our topic today. Steve has been involved in embedded database architecture and engineering for over 20 years and brings a wealth of experience in solving real-world problems in the arena. Steve?
Okay, thanks, Chris, and thanks, Ted. Got a lot of information to cover today, so let's just jump right into it. Embedded database is a term that the industry coined in the 1980s to mean a database that's embedded into the application, in contrast to a client-server database architecture in which the database server stands alone as its own process or multiple processes in the operating system, and client applications connect to it through some inter-process communication protocol. An embedded database, then, is one that was delivered to the application programmer in the form of a library or an archive of object code modules to be linked with the application code to create a complete application program. In this sense, the database runtime code coexists with the application, runs in the same address space, and can be called in process. Early in this decade, there was an effort to give embedded databases a new name, application-specific databases, but this never really caught on. That's kind of unfortunate because it would have addressed some of the confusion about the term embedded database that has arisen since the term was first used in the 1980s. Some of that confusion derives from the term embedded database having come to mean virtually any non-enterprise database system. It's almost like if it's not Oracle, DB2, SQL Server, or Sybase, it's an embedded database, regardless of any of its characteristics. Starting in the late 1990s, we started to see adoption of embedded databases in embedded systems, which further muddied the waters. Now many people associate embedded databases with embedded systems. It's not too surprising because this is where the significant growth is in the database market. The enterprise database market has been relatively stagnant for a long time. So all the buzz and excitement about database systems seems to be in the embedded system space. One thing we can agree on with regard to embedded databases is that they are generally used to gain greater efficiency and responsiveness, higher throughput, and lower administration requirements than their bigger cousins for all types of systems that require database management services, but which don't lend themselves to an enterprise-class database. Examples are all around us, such as your copy of Quicken for your personal finances, which happens to be a Sybase SQL Anywhere solution, various mobile CRM packages for Road Warriors laptops that typically use the Lite version of a CRM database, for example, Oracle Lite, portable media players like JVC's Alneo line of portable media players, which happens to be an ExtremeDB solution, and certain financial applications like algorithmic trading. And incidentally, financial applications are fertile ground for in-memory databases like ExtremeDB and Oracle's x10, and also various network equipment like F5 networks and Big IP application traffic management switches, which also happens to be an ExtremeDB application. Network equipment vendors have been frequent adopters of ExtremeDB and Oracle's BerkeleyDB. Throughout the presentation today, I'll be using the terms table, record type, and class interchangeably, likewise row, record instance, and object interchangeably, and column and field. One differentiator of some embedded databases is that they don't necessarily fit the definition of a relational database. Some do, some can but don't have to, and some just cannot. For those that don't have to or cannot be treated as a relational database, database administrators almost universally view this as a bad thing. But that's not necessarily so. For example, embedded systems commonly operate with CPUs that have a fraction of the processing power of today's desktops, and yet they need to respond to real-time events. In some cases, it just isn't possible to spend the CPU cycles needed to decompose a complex data structure into a normalized form for storage in a relational database, and or to recompose the data on retrieval into its native complex form. You'd rather just store it and retrieve it in its complex form. Embedded databases like MySQL, Solid, and x10 that have SQL as their primary or their only interface fall easily into the relational bucket. Databases like ExtremeDB and Rayma's RDM don't prevent you from using the database in the same relational way as you would Oracle, MySQL, and the others, but they also don't force you to do so. They permit denormalized data structures such as arrays, and first normal form requires that a data model have no repeating groups of data items, and an array is definitely a repeating group of data items, so it's decidedly non-relational. Anyone would be hard-pressed to describe a database like Oracle's BerkeleyDB as relational or any other model because it offers no data definition language. It permits you to store any name-value pair combination. And then there's object-oriented databases like our own PERST and Versant's DB4.0 that are designed to work as nearly transparently as possible with object-oriented languages like Java and C#. The size of the embedded database market, as reported by IDC, is nearly $1.8 billion. Now, that includes some very large vendors that most folks don't think of when you say the words embedded database, including, obviously, Oracle with Oracle Lite, x10, and BerkeleyDB. I've listed here the names of some of the database vendors that most frequently come to mind, and in fact, they dominate the top 20 native search results for the term embedded database. The same study shows that the embedded database market is divided roughly in half, with North America representing almost half of the worldwide market, and the rest of the world representing the other half. That division of revenue is more or less borne out by McObject's experience as well. Where we part company with the IDC study is with respect to the breakdown by operating system. For embedded database products other than the light versions of the enterprise databases, there's much more emphasis on Linux and embedded or real-time operating systems. It's difficult to compete with, for example, Microsoft SQL Server Express, which certainly has a high cost of ownership, but no upfront licensing costs. It's free. Companies that have historically offered client-server SQL databases that are suitable for departmental computing have found it increasingly difficult to compete. Embedded databases can be divided into many different groups that we'll explore over the next several slides. One such grouping is those embedded databases that support SQL as a database interface and those that offer a navigational programming interface. SQL has several advantages. Perhaps most obvious is its familiarity. It's the lingua franca of databases. This is further enhanced by the ODBC API. SQL also possesses great expressiveness. In other words, as a database programmer, I can fairly succinctly express a pretty complex query that, for example, joins three tables, calculates some scalar values or aggregate values based on groupings, filters the data to only those rows that satisfy certain conditions, and then sort the results. Likewise, a simple SQL update or delete statement can operate as easily on 1, 10, or 10,000 rows in the database. That expressiveness can be a detriment, though, too. Like most systems, SQL's complexity has grown. Things never get more simple, and it's possible to fashion a SQL statement that only the most sophisticated SQL programmer could decipher. Another potential downside is that SQL is a black box. By that I mean we as programmers submit our SQL statement to the database engine, and how the database engine goes about processing or executing that SQL statement is largely transparent to us, and by default we have no control over it. Some embedded database vendors give you a means to take control, for example by providing hints to the SQL optimizer by embedding special characters or special keywords into the SQL statement that tell the optimizer to use a specific index or to navigate a certain table. But once you go down that path by embedding these special characters or special keywords, you become locked into that database vendor. And vendor independence is one of the perceived benefits of SQL. SQL is almost always an interpreted language, meaning that it's parsed at runtime, not at compile time. Once parsed, then the optimizer kicks in to determine the most efficient plan to carry out the operations that are implied by the SQL statement. The result's called the execution plan. And then finally, the execution plan is carried out. All this processing consumes CPU cycles, of course, and may also involve some file I/O, for example, to retrieve database statistics on row counts, index histograms, and so on that the optimizer uses to help calculate the cost of possible execution plan steps. So SQL automatically carries a performance penalty due to the work that has to be done before the work implied by the SQL statement itself can be carried out. The optimizers themselves come in two forms: cost-based optimizers and rule-based optimizers. A cost-based optimizer is inherently more complex, and it's more of a black box, and it can be a very delicate bit of software. Cost-based optimizers attempt to calculate the cost of each possible way of executing one step in the execution plan, and then assemble a sequence of steps that is less costly than any other combination of steps. When they work well, but there are some potential problems to watch out for. First, the number of possible execution plan steps can be enormous, and then the number of possible combinations of this enormous number of steps can be truly mind-boggling. And the consequence is that your program can spend an unacceptably long time in the optimizer considering all the options. Now here again, database vendors typically offer a way out by allowing you to instruct the optimizer to take the best plan so far after considering the first 100,000 plans or after 500 milliseconds or some other criteria. Another side effect of cost-based optimizers is that the execution plan of an unchanging query can change from one execution to the next as the database statistics change. In other words, the row counts for various tables or the index histograms, which causes the cost-based optimizer to calculate different costs for different steps and ultimately come up with a different execution plan. So what was acceptable performance for a query in the QA lab based upon the anticipated distribution of data and discrete values turns out to be unacceptable in the field with live data that's markedly different from the data that was used in the QA lab. And then finally, seemingly innocent changes to the SQL optimizer logic by the database vendor can have disastrous effects on the performance of queries that ran fine before the supposedly improved optimizer was deployed. Now, rule-based optimizers are simpler, and they solve the problems that I just described above. A rule-based optimizer applies a fixed set of rules to formulate the execution plan, and the time required to formulate the execution plan is consistent as long as the rules don't change. In other words, the rule-based optimizer isn't going to spin for an indeterminate amount of time considering umpteen gazillion different execution plans. And its execution plan will never change just because of the distribution of data in the database changed, because that isn't considered. You don't have to give the optimizer hints. You only have to understand the rules and then formulate your SQL statement in such a way that the optimizer will produce the right execution plan. Navigational APIs bypass SQL altogether. The term navigational derives from the way the application programmer interacts with the database in the application source code. The application navigates, if you will, through the database one record at a time. Contrast this with SQL, which is a set-oriented language. In other words, an SQL statement operates on a set of rows in the database, or in the case of a query, returns a result set to the application. With the navigational programming interface, a typical sequence of events would be to use a function to locate a record, row, or object of interest in the database. For example, perform an index lookup to find a row by some value, or to find an object by its object identifier, and then act on that row, maybe read its values for display, update a field, or delete the row, or whatever, and then get the next record and repeat. So you're navigating through the database one record at a time. Navigational APIs always outperform SQL. Even the best SQL can't avoid the overhead of parsing, optimizing, and executing the plan. A navigational API goes directly to the database tables. Consequently, a navigational API is many times faster. Exactly how much faster depends on the specific operations and the database vendor, but 3 to 4 times faster is a reasonable expectation. A navigational API is, by its nature, more deterministic or more predictable than SQL. And this goes back to SQL being a black box, whereas with the navigational API, you are directly controlling the interactions with the database. However, navigational APIs are by definition proprietary. There's no industry or de facto standards for navigational APIs. There are similarities between some of the embedded database vendors' navigational APIs, but that's about as far as it goes. For example, RDM has a function call called d_read, and Faircom's C-tree has a function called readdata. But they perform essentially the same function, but the steps required before you can call either function and the arguments you pass to either function are not at all similar. And finally, some embedded databases support both SQL and navigational APIs, and you can use both APIs with the same database and within the same application. This gives you the flexibility to use SQL when its expressiveness is advantageous and maximum performance is not required, while using the navigational API when SQL's expressiveness is not a factor or when maximum performance is required. ExtremeDB and Rama's RDM fall into this category. Embedded databases that support the SQL language usually also support the SQL data definition language, for example, the create table statement. Embedded databases with a navigational API may or may not have a data definition language. For example, BerkeleyDB does not. You just store opaque name-value pairs in the database, and it's up to the application program to interpret the data, and it's up to the application programmers to diligently document what's being stored in the database. Databases that supported a data definition language, the data definition language itself provides that documentation. In the absence of it, it's up to the developers to provide that documentation. Faircom's C-tree uses the host programming language, specifically C structures, to define the database contents. And still other embedded databases like ExtremeDB and Rama's RDM have their own proprietary data definition language. And ExtremeDB can optionally use the SQL data definition language. So this slide shows a simple 3-table database schema defined with SQL data definition language on the left and the ExtremeDB proprietary data definition language, so you can compare the two by looking at them side by side. SQL and proprietary data definition languages generally follow the same form, as you can see here. The details differ, but the essence of it is really the same. This example defines a database that would gather website usage statistics. The website has URLs and visitors. A given URL can be visited by many visitors, and a given visitor can visit many different URLs. Therefore, what we have is a many-to-many relationship, which is modeled as two one-to-many relationships with an intersect record between them that we call visit in our example. So the many-to-many relationship between URL and visitor becomes two assertions that we model in the database. The first assertion is that a URL has many visits, and a visit is to one URL. And the second assertion is a visitor has many visits, and a visit is by one visitor. There's a perception that the expressiveness of SQL results in more productive programmers. In other words, that SQL is assuming most of the workload from the programmer. But this isn't necessarily so. It can be true with relatively complex SQL statements, but it's equally not true for relatively simple SQL statements. So on this slide, we see the ODBC SQL implementation of a three-table join. Select some list of columns from URL, visitor, visit, with the join conditions and an order by clause. The ODBC programmer is required to make several steps to execute the query. You have to allocate a statement handle, prepare the statement handle, parse and optimize it, bind the host variables to receive the column values of the result set, execute the statement, fetch the results, and free the statement handle. Now this slide shows the ExtremeDB Navigational API equivalent of the ODBC SQL code that we saw on the previous slide. And as you can see, the quantity of code to accomplish the same three-table join with a sort is about the same. In this case, the programmer has to start a transaction, which we see in red, instantiate the cursors that are going to be used to affect the table joins, which is in yellow, and then within a couple of loops, retrieve the rows of interest from the tables. The first loop, which is in pale green, sets up an index scan that accomplishes the same result as the SQL condition order by vname. The cursor points to each entry in the index in turn. For each, we get a handle to the row that's referenced by the index entry, and we get the value of the vname field from it, which we see in dark green. We use that vname value as a search value to join the visit record. In relational terms, vname is a foreign key, and that's in light blue. For each visit record that we find, we compare the foreign key of the record pointed at by the cursor to the search value. When they're different, we break the loop because we completed the join. That's also in light blue. Otherwise, we have a join, and we get a handle to the visit record, extract its path field, which is a foreign key of the URL table, and use it to accomplish the join to the primary key of the URL table, and that's the purple text. The sequence of steps that I just outlined is exactly what SQL does inside its black box. The only difference is you're taking direct control and doing it yourself. On this page, we have graphs of the performance of the ExtremeDB Navigational API on the top and the ExtremeSQL ODBC API on the bottom for the same operation, in this case, a single table scan. There's a web link to the white paper that I extracted this from at the bottom of the screen there. This test was conducted on an SGI Altix 4700 supercomputer with 80 dual-core Itanium processors running at 1.6 gigahertz and 4 terabytes of memory. We created an in-memory database that was about 1.2 terabytes and then ran some tests to determine how effectively ExtremeDB and the Altix could scale from one thread to 160 threads on that 160 cores. You can see that the performance of the Navigational API is 3 to 4 times better than SQL for the reasons that I described before. The slopes of the lines from 1 to 80 to 160 threads are different, we think because the ratio of overhead imposed by SQL to the system overhead involved with 80 versus 160 threads is greater at 80 threads. Conversely, without SQL, there's little difference between 1 and 80 threads, but we started to really tax the system more at 160 threads. Even so, having 160 queries each execute under 2 microseconds yields over 87 million queries per second. And then SQL wasn't too shabby either at greater than 26 million queries per second. Another way that we can divide the embedded database market is along the lines of in-memory databases and on-disk databases. On-disk databases include the vast majority of embedded databases that are available. They provide automatic persistence of varying degrees. In the database world, we talk about database transactions that have the ACID properties. First, a transaction is a unit of work that should all succeed or fail together. A common example is transferring money between bank accounts. You don't want the money to be withdrawn from the first bank account and then have the transaction fail before the money is deposited to the second transaction account. This unit of work should all succeed or fail together. ACID is an acronym for atomicity, consistency, isolation, and durability. Atomicity is that all-or-nothing property that I just described. Consistency states that the database should be in a consistent state at the completion of a transaction. In other words, applying a transaction to the database should move the database from one consistent state to another consistent state. Isolation means that a thread or a process cannot see the changes being made by another thread or process until those changes are committed to the database. And finally, durability means that once the transaction commit is complete, then the transaction is durable. In other words, it can be recovered if there's a system failure or a crash. And here's the connection to my introduction with reference to the phrase automatic persistence. Some on-disk databases allow you to bypass transactions altogether, such as the Berkeley DB concurrent data store, and RDM configured to run without transactions. And some database systems allow you to configure the system to run with asynchronous transactions, including ExtremeDB. Transaction processing carries pretty significant overhead for on-disk databases. To be durable, the changes made within a transaction have to be flushed through the database cache and the file system cache and get physically onto the media, and that's an expensive operation. So running without transactions or running with asynchronous transactions that don't force the flush will significantly improve performance. The point with respect to the assumed automatic persistence of on-disk databases is don't make that assumption. Just because a database system stores the database on a file system alone does not guarantee 100% persistence. You've also got to make sure that transactions with the ACID properties are being utilized. That said, there are times when ACID properties are not required. For example, during a bulk load process with an empty database. If the load fails, it may be the case that it can just be started over. In that case, having a significantly faster load process might outweigh the risk of having to start over if something goes wrong. Similarly, asynchronous transactions may be acceptable if it's judged that greater performance outweighs transaction durability. We see this sometimes in the financial markets where performance is crucial and the customer knows that in a worst-case scenario, if they lost a few transactions, they could reconstruct the data from other sources, such as going back to the exchange and getting the buy-sell order executions. There are different ways of implementing ACID transactions. For example, there are undo and redo transaction policies in ExtremeDB. You can choose between them. The undo transaction policy is shared, for example, by the RAMA RDM embedded database system. With this policy, information is kept by the database runtime to be able to undo any changes made during the transaction if the transaction is aborted or the application fails before committing or aborting the transaction. Undo transactions require more write operations to the file system, and in the case of ExtremeDB, they can require less memory, and in any implementation, you don't need to be concerned about growing transaction log files. Each new transaction overwrites the last transaction because that undo information is no longer needed after the last transaction is either committed or aborted, so it's just overwritten by the next transaction. So the database log file doesn't grow and grow and grow. Therefore, there can be less database administration with the undo transaction policy. The redo transaction policy is probably what's most familiar to most people. It's also called write-ahead logging. With redo transactions, we keep a running log file of database transactions since a point in time that we'll call a checkpoint. If the system fails, the database can be restored from the last checkpoint, and then the transaction log replayed to redo each of the subsequent committed transactions, and that's where the name redo transactions comes from. Redo transaction logging can involve less file system write operations than undo logging, but might require more memory if you have very long-running transactions. Generally speaking, all on-disk databases trade CPU cycles and memory consumption to avoid file I/O. As I mentioned previously, file I/O is the most expensive operation for an on-disk database. Disk access is always measured in milliseconds, whereas CPU and memory access is measured in nanoseconds or microseconds. So it makes sense to use extra CPU cycles and to consume more memory if it allows you to avoid additional disk I/O. It's a good trade-off. Consequently, on-disk databases have a lot of complex logic to create and maintain a cache of frequently accessed data and or indexes. Maintaining the cache involves exactly that trade-off. It uses CPU cycles and the cache itself takes up memory. Also, the extra complexity results in database system code that is larger, so the footprint of on-disk databases is usually larger than in-memory databases. On-disk databases also organize their indexes differently than in-memory databases do. On-disk database indexes contain a redundant copy of the indexed data. For example, if you've got a customer table that has an index on customer name, and a query like select customer name from customer order by customer name, that can be satisfied by just scanning the index. If the data wasn't in the index, then you'd need one additional file read per customer record to retrieve the customer name from the data file. So on-disk databases are also larger because they have this redundant copy of the data in the indexes. But disk space is relatively cheap, certainly cheaper than memory, so the trade-off to avoid that additional disk I/O is reasonable. In-memory databases really started to become popular in the mid to late 90s as the cost of memory started to fall and the density of memory increased. Initially, in-memory databases were all large, complex systems that were designed for PCs and servers with ample processing power and memory. Times 10 and Polyhedra were pioneers in this area. McObject pushed the boundary of in-memory databases to deeply embedded systems with the introduction of ExtremeDB in 2001. Whereas Polyhedra and Times 10 are relatively large and complex database systems with code sizes of several megabytes, ExtremeDB is a compact in-memory database system with a code size ranging from 100 to 150K. There are other small footprint in-memory databases available now, but no others offer the depth of features or the platform support of ExtremeDB. In-memory databases are tremendously faster than on-disk databases for the obvious reason. There's no file I/O. But furthermore, in-memory database systems are just optimized differently than on-disk databases. As I mentioned, on-disk databases are optimized to minimize disk I/O. In-memory database systems are optimized to reduce memory consumption and, at least in the case of ExtremeDB, CPU cycles. Unlike their on-disk cousins, in-memory databases cannot assume that storage space is cheap and plentiful, and there's no need to trade CPU or memory to avoid disk I/O because, of course, there is no disk I/O. So, for example, an in-memory database system doesn't keep redundant data in its indexes. Consequently, whereas 1 megabyte of raw data could require 2 to 10 megabytes of disk space for an on-disk database, that same 1 megabyte of raw data might require only 1.2 to 2 megabytes of space for an in-memory database. Obviously, persistence is not automatic with in-memory databases. Because the database is stored in RAM, and RAM is volatile, if the system loses power, then the database is lost. Different in-memory database vendors have different ways of addressing this, which include support for battery-backed RAM, transaction logging, and high availability. Battery-backed RAM doesn't lose its content if the power fails, if the main power fails, because you got the battery backup. So on restart, the database system can simply reattach to the memory address, perform any cleanup necessary, and then resume processing. Transaction logging introduces some file I/O, but it's less than a full-on on-disk database. And it's one way to give persistence to in-memory databases. With high availability, 2 or more copies of the database are kept in 2 hardware instances so that if the primary database system host fails, there's a standby copy ready to take over. Finally, for many classes of applications, you just don't care about persistence. For example, the TV guide in your set-top box. If you lose power at your house, the set-top box is going to get a new TV guide from the satellite transponder or from the cable head end. Network routers are another example. They get the routing table information from their peers on the network. so they also have no need for a persistent database. In-memory databases can have a simpler architecture than on-disk databases. This is particularly true of truly embedded in-memory databases, in other words, those that are delivered as a library versus a client-server architecture. There's no cache logic, there's no file I/O, there's no inter-process communication, and so on. This is why an in-memory embedded database system can be as little as 100K in code size. This might beg the question for some, if it's so darn simple, why don't I just write it myself? Well, some people do, mistakenly thinking that simpler is the same as simple. And it's not, of course. The in-memory database still has to manage concurrency, implement ACID transactions, provide robust indexing, excellent memory management, and a host of other capabilities. For the reasons I just described, an in-memory embedded database, can also be more deterministic or real-time-ish. The architecture eliminates the unpredictable nature of a cache hit or a cache miss. There's no rotational latency associated with a hard disk, where rotational latency is waiting for the disk head to slew back and forth or waiting for the platter to spin to the right location. And there's no inter-process communication, so there's no unpredictable network latency. Lastly, on-disk databases tend to get slower as they grow in size, which is another variety of unpredictability. This is largely due to the indexes growing deeper. If a B-tree index is 6 levels deep, then on average you're going to need 3 seek operations to find any given value. But in a worst-case scenario, you'll need 6 seek operations, and in a best-case scenario, you'll need just 1 seek operation if you find it at the root node. That's yet another dimension of unpredictability with on-disk databases. And then the deeper the index, the more seek operations that are required. So as the database grows over time and the indexes get deeper, it gets slower because it needs more seek operations on average. On-disk B-trees grow deep faster because of that redundant data that's stored in each slot of the index. In-memory indexes, conversely, don't have that redundant data, so they don't grow deep as fast. Consequently, in-memory databases have a more shallow performance slope as the database grows in size. And now there are hybrid database systems that combine in-memory and on-disk database system capabilities in a single product. Examples are ExtremeDB Fusion and Solids Database, which is actually now part of IBM. There are differences, so examine each product's capabilities. For example, can the system support both in-memory and on-disk tables within the same database definition, or does it have to be all in-memory or all on-disk? Finally, for some uses, the choice of in-memory or on-disk or a hybrid solution might be dictated by the form factor and or the bill of materials cost requirements. So-called spinning memory is far more dense, and while the cost of RAM is coming down, spinning memory is still less expensive. If you need to pack 80 gigabytes of memory into an iPod-like device, you pretty much have to go with a microdrive for both form factor and cost considerations. One of the bullet points on the previous slide that I didn't talk about is this. You can't take an on-disk database system and create the database in a RAM drive and expect to get the same performance as an in-memory database. As I described before, on-disk database systems have a lot of complex logic built into them to avoid disk I/O, largely revolving around creating and maintaining a database cache. All the processing to determine if a requested record is in the cache, to bring it into the cache if it's not, to determine what to purge from the cache if the cache is already full, and to maintain consistency between the cache and the physical storage is all still present, even if the database is in a RAM drive. The on-disk database management system is ignorant of the storage media. It just looks like a file system. It doesn't know if it's a file system in RAM, on flash, or spinning memory. Another key difference that was alluded to before is the amount of memory needed to store that database. With a RAM drive, you're going to need just as much file space as if the database was stored on a spinning disk, even though file space, in this case, is memory. So on this slide, we have a graph that shows the relative performance of ExtremeDB and an on-disk database, DB Linux in this case, with the database files in a RAM drive. This particular test was run on Red Hat Linux with a 400 megahertz Celeron processor with just 128 megabytes of RAM, which looks like it has the characteristics of a lot of embedded systems that we see, relatively modest resources. And then we measured the time to read and write 30,000 records. There is a very large difference in performance for writes because of all the file system overhead, and the database system, as I said, doesn't know it's operating in a RAM drive, and it still wants to journal transactions, flush the file system buffers, and so on. All the processing associated with trying to save file I/O for a non-disk database just gets in the way when, in fact, the file system is in memory. The embedded database market can also be divided along the lines of truly embedded and client-server application-specific database systems. I've touched on most of these points already, so we'll just briefly summarize here. A truly embedded database is a library that's linked with the application code into a single executable program image, so the database runtime is in the same address space. In other words, it's in process. This eliminates the inter-process communication that's needed by a client-server architecture. The architecture is simpler because all the communication logic is eliminated, as well as the logic to create and maintain connection pools, user authentication, permissions, scheduling, and so on. There's also far less administration required for an embedded database. There's no concept of users, so there's no need to create user credentials, grant and invoke permissions, and other activities related to user account management. On the downside, a truly embedded database system might, and I emphasize might, be less able to support very large communities of current threads, processes, users, etc. Though it's all relative. I mean, how should we define large? And it's also somewhat dependent on the application's characteristics, the size of the database, the ratio of readers to writers, overall performance requirements, and so on. Conversely, client-server database systems have their strengths as well. Since more of the processing load is on the server, the clients can be thinner. It facilitates centralized processing. In other words, we can deploy chunks of business logic within the server as stored procedures. This can make one aspect of administration easier. If the business rules change, then the code only needs to be changed in one place, in the stored procedure, and all the clients are automatically going to inherit that change. And client-server systems have the potential to scale up better and to better leverage SMP and or multi-core systems. Some client-server implementations have the ability to automatically spawn additional threads as the number of connected clients grows. And these threads can be easily scheduled by the operating system to take advantage of available CPUs or cores. Another advantage that's claimed by embedded database vendors is so-called zero administration. In fact, what they mean is no DBA required, not that there's no administration required. Embedded database systems typically require less administration than a full-on enterprise database, and the administrative requirements can usually be wrapped up in the application by calling application programming interfaces versus using a separate DBMS vendor-provided administration tool or a dashboard or whatever. The administrative requirements of embedded databases vary according to the database architecture or model, with client-server systems requiring the most administration, followed by embedded on-disk database systems, and then lastly with truly embedded in-memory database systems requiring the least amount of administration. So why not just use the light versions of Oracle, IBM, or Microsoft's databases? One obvious answer is that the embedded database vendors like McObject specialize. For example, ExtremeDB and our open source Java and .NET database First offer a variety of indexes that you can't find in Oracle Lite and products like that. We have R-tree indexes for geospatial requirements. We have Patricia tree indexes for network and telecommunication systems, for example. Some embedded database vendors are also less dogmatic about the relational model, which could be important to you. Another example of this last point is object-oriented databases, such as our own PERST and Versant's DB4O, which are two open-source dual-license object databases that can be excellent choices of embedded databases when you're programming in Java or C# and you want to avoid the fabled impedance mismatch of storing objects in relational databases. PERST and DB4O are quite happy to store POJOs or plain old Java objects. If you're developing a system that will be deployed on any of the many embedded and real-time operating systems, such as VxWorks, Integrity, Nucleus, QNX, and many more, then the big four database vendors will have been eliminated by default because they're simply not available on those platforms. Another major motivation is for better performance, regardless of database size or the platform's capability or lack of capability. For a dedicated application, and remember the term application-specific database, an embedded database is usually going to outperform the enterprise databases. Even on a platform like Windows CE, where the enterprise database vendors do offer their light versions, an embedded database might still be a superior choice if the target platform has limited CPU power. And an in-memory database might be a particularly good choice because of the optimization emphasis on reducing CPU cycles and minimizing memory consumption. Finally, embedded database companies such as ourselves are relatively small, certainly compared to Oracle, for example, and tend to be focused on our customers' needs. It isn't uncommon that our developers engage directly with our customers. You don't get that one-on-one interaction with an enterprise database vendor. And we're also light on our feet, meaning that we can be very responsive to our customers' needs. We're not locked into rigid corporate policies that dictate lengthy cycles of market research, marketing requirements documents, and so on and so forth. Embedded databases started in business applications, and they're still popular in these domains. But as I said before, the excitement is in what we generically call embedded systems. At MacObject, ExtremeDB has been popular in network and telecommunication systems, consumer electronics, military and aerospace, and industrial control, with a few representative customer names mentioned here for each of those markets. ExtremeDB has also enjoyed success in one key business application vertical market, that being financial services. Due to the high performance of our in-memory database and its ability to store more data in any given amount of memory, companies in New York, Chicago, Vancouver, and China have adopted ExtremeDB to support their algorithmic trading, arbitrage trading, exchange order book systems, and stock ticker plants. So we've reached the end of my presentation. To quickly summarize, the term embedded database encompasses everything from Oracle Lite to ExtremeDB. Embedded database technology runs the gamut, including in-memory, on disk, and all the variations that are listed here. The architecture and technology leads to significant differences in code size, runtime footprint, performance, predictability, administrative requirements, scalability, and portability. Understanding the requirements of your system will help you narrow the field of database systems to a manageable few that you can zero in on for evaluation. So at this point, we have a few minutes left for questions, so I'll turn it back over to Ted to moderate the question and answer session.
Thanks, Steve. And we would like to take some questions from the audience now. You can type and send your questions from the Q&A box on the lower right side of your control panel. And one question that's come in is, are there any performance advantages to be gained by defining a database using the proprietary schema language if I'm going to use SQL to perform most database operations?
Well, there could be. More often than not, though, the proprietary data definition language is used in order to take advantage of database system features that can only be exposed through the vendor's proprietary data definition language, because there is no standard SQL syntax for defining those features, unless the vendor has extended the SQL language but there could be performance implications as well. For example, as I mentioned, both ExtremeDB and RAMA RDM allow you to store arrays of scalar values in the database. And in the relational world, you would have to normalize that into a one-to-many relationship. In the case of ExtremeDB, we've extended the SQL syntax to allow you to insert or update or select values from a table that has a field as an array. So that would certainly be a performance implication there.
All right. Are there additional questions? We can take them. And one that's come in is, you mentioned that client-server databases can likely scale more than in-process databases. Now, does this refer to the scalability and number of users accessing the database at one time, or to the maximum size of the database?
Well, I was really referring more to the ability to support concurrent connections. Whether a database system is, so assuming that a database system is maintaining a database on some persistent media, then it doesn't matter if that database system is embedded or client-server. Its capacity really depends on the storage system. So if you're on a storage area network that has petabytes of storage, it doesn't matter if your database system is embedded or client-server, it can take advantage of that storage space. And then with reference to the number of concurrent connections, it's possible, although it's not a foregone conclusion, but it's possible that a client-server system would be able to scale better on a multi-core system. As I mentioned, some client-server systems are sophisticated enough to be able to automatically spawn new threads when the number of connections to the database server increases, and then the operating system can schedule those threads. Embedded databases are passive in nature. They're a library. There's not independently running code, so they're not going to automatically spawn threads. It would be up to the application code to spawn threads as necessary. So the responsibility shifts from the database management system to the application, but that doesn't mean that the database system is unable to scale. It just is dependent on the application developer building that scalability in.
All right. Additional questions? You can enter them in the Q&A panel on the lower right side of your screen. And one that's come in is, you discussed, again, in-process databases and their advantages and disadvantages relative to client-server architectures. My application needs to access the database over a network. Is in-process still an option?
Well, it depends on the vendors. So I can talk about our products. So we have embedded databases, but we also provide remote APIs so that a process on node B of the network can use a database that's being hosted on node A of the network. So even though it's not a client-server architecture, you can still have multiple nodes on a network sharing a common database that's stored on yet another node of the network. And that doesn't matter if it's an in-memory or an on-disk database.
Additional questions from anyone? Here's one. Your slide used the word deterministic in connection with the ExtremeDB database. Can you explain more about that?
Okay. So an in-memory database in particular can be more deterministic. Let me clarify that. An in-memory embedded database can be more deterministic than the other architectures when you're using a navigational API. So those three attributes together, in-memory, embedded database with a navigational API. So with in-memory, you're eliminating all of the unpredictable latencies associated with file I/O. It's embedded, so you're eliminating the unpredictable latencies associated with network communication that is necessary with the client-server architecture. And then the navigational API is eliminating the unpredictability that's associated with SQL. So those three attributes together are going to give you the most determinism rather. And then any other combination will give you varying degrees of determinism, but less than those three characteristics put together.
All right. Any additional questions? Well, then it looks like we've come to the end of our event today. If you do have any questions, feel free to contact us at the email addresses shown on the screen. And also do stop by our new Facebook page. If you go to macobject.com/Facebook, you'll be redirected there. And there's an item for this webinar on that page. You can leave comments or any questions there as well. And thanks for attending today. We hope you've gained a good understanding of how key data management choices can significantly affect your application's performance, efficiency, reliability, and time to market. As you've seen, different techniques and technologies can be applied to managing information in real-time software, and your choices at the start of a project will definitely affect the results. We'll be holding follow-on sessions in the upcoming weeks, and look forward to you joining us then. And please visit our website for more excellent white papers, articles, recordings of this and other webinars. This one should be available there in the next 48 hours. We'll be holding follow-on sessions in the upcoming weeks, and look forward to you joining us then.